Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, so now the theorem I want to prove about Dedekind domains is the following. We will go little bit backwards. So this is the theorem I want to prove. This will characterize and this will also not this, but yeah, this is the characterization of Dedekind domain. So let A be a Noetherian integral domain then the following are equivalent. 1 A is DD Dedekind domain, so that is A is normal of dimension less equal to 1. 2 AP, every localization A localized at P is a DVR for every non-zero prime ideal. And third, these are the new terms, every fractionary ideal of A is invertible. So I will define these terms and then we will prove the equivalence of this, and as a corollary we will deduce the theorem that I mentioned, that every ideal is a product of prime ideals in a essentially in a unique way in a Dedekind domain. Okay, so let us digress a little bit about fractionary ideals and invertible ideals. So fractionary ideals and invertible ideals. So we will assume always A is an integral domain. And K is its quotient field. So we have K here and we have A here. A fractionary ideal means, so this should correspond to the fractions in the usual integers. So that means they are elements of, and fractions are elements. So fractionary ideals should be the ideals corresponding to the fractions, right. So fractionary ideal means fractionary ideal in A is a non-zero submodule, A submodule of K which has a common denominator, which has a common denominator. That simply means, that is, it's a submodule. I keep writing A, this is now not an ideal. So it's a submodule of K and it has a common denominator, means if I multiply by that, it should go inside A. So, there exists a D non-zero, D in A, D non-zero with D times this German A is contained in A actually. So, that means the D times A is actually an ideal in A. So, this A is not A may not be an ideal, it is a submodule of K, but if I multiply by one non-zero element, it becomes an ideal in A. So, this is ideal in A. All right. So, that is the fractionary ideal. Now, there is look at the easy properties of the fractionary ideals. First of all, if A is a fraction, so I will introduce a notation. Fractionary ideals usually denoted by F of A. This is a set of all fractionary ideals. Ideals in A. Alright, so obviously the principal, the submodule of K generated by one element, they are obviously fractionary ideal, because that denominator really is the denominator. Also the ideal, the submodule A submodule A is also fractionary. So, A is an element here, also the principal submodule, the cyclic submodules A by B, this is also fractionary, because this B is a really denominator. More generally, if I have two fractionary ideals A and B, then their product is also fractionary ideal. A times B is also fractionary ideal. A times B makes sense because everything is happening in the field K. So, the product is the, see, normally you cannot multiply two submodules, two modules, but these are very special modules, they are contained in K. So, if D is a common denominator of A, D prime is a common denominator of B, then D times D prime will be common denominator of the product. Okay. So, the product, okay. So, therefore, this one, this FA with the product, this becomes semigroup. Semigroup simply means that there is a product operation and it is associative, but it is more than a semigroup, it also has the identity element, namely capital A is the identity element. So, this is indeed a monoid under multiplication. A is the identity element, A is the neutral element. So, whenever we have a monoid, we look at the elements in that monoid which are invertible. So, those guys are called invertible ideals. So, the name also is very clear. So, and a fractionary ideal FA in FA is called invertible if A has inverse or A is invertible in the monoid FA under multiplication. So, what does that mean? So, that is there exists an element B here, so that the product is A. So, that is there exists another fractionary ideal B in FA with A times B equal to A, also it is B times A, and such a B will be unique then. and that unique is denoted by A inverse. So, that B is unique denoted by A inverse. So, we want to guess who is that who is this B in terms of A, and that will be. So, for example, if your fractionary ideal were principal generated by X, let me call it. Suppose this was a principal fractionary ideal, then who will be the inverse of A? Then obviously A inverse will be generated by X inverse. X inverse makes sense, this X is a non-zero element. So, the zero ideal cannot be fractionary ideal. So, therefore, this is the. So, we want to guess who will be the inverse. So, obviously, so we have given this A fractionary ideal. So, note that, so we want somebody whose product with that is equal to A. So, look at this colon operation, A colon A. This is what? This is by definition all those elements in the quotient field. This is happening in the quotient field because A is a submodule of capital K. So, all those elements in the field such that when I multiply by this ideal you get inside A. So, X times A is contained in A. This is the colon ideal. So, first of all note that this is again fractionary. So, to say that it is again fractionary, what do we have to show? It also has a common denominator. So, given a common denominator of A, we want to find a common denominator of for this. So, that is, so suppose you are given D, which is a common denominator for A, that means T times A is contained in A. So, suppose if for some D in A is, then what does this mean? So, that means then this D will belong to this colon ideal. And then this is non-zero, in particular this colon ideal is non-zero because D is there. Now, any element of A, I claim it is a common denominator for this colon ideal. Then, and every non-zero element A in A is a common denominator for this. That means, what should I check? That this A times A colon ideal should be contained in A, but that is obvious. So, therefore, every non-zero element is a common denominator. So, what did we prove? We proved that assuming A fractionary ideal, this colon ideal is also fractionary ideal. So, it is, so we have proved that if A is a fractionary ideal, then colon A is also fractionary ideal. So, obviously, we want to now check that this guy is the right inverse. This A colon the German ideal, the A colon the Gothic A, this is the inverse of this. This is what we would like to check, because this is a candidate and also the product is contained in A. So, therefore, we will prove the following lemma. All right. So, for a fractionary ideal A, the following are equivalent. 1, A is invertible. So, just to remember that is FA, A belongs to FA cross here. Remember that was our standard notation to denote units in a monoid in general. So, this is 1, 2 is this Gotik A times the colon A, this product is actually equal to A. If you prove this, then this has to be the inverse of this, because the operation is commutative. So, this will also become equal to this, or you can use instead of A, you can replace the A by the colon ideally, and then the colon of colon A will be A. So, this is 2, 3 is so what does this mean? This equality should mean what? This product is A, that means 1 should be a combination of this. So, there exist some elements x1 to xr in the Gotik A and y1 to yr in the colon with the product x1 y1 plus xr yr equal to 1. So, further just to summarize of these 3 and then we will prove that all the equivalent. So, further if any one of 1, 2, 3 holds, then A inverse equal to A colon A, and A is generated as a module by this x1 to xr, and inverse is generated by y1 to yr. This is generated by y1 to yr. So, proof. We will prove 1 implies 2 implies 3 implies 1, 1 implies 2 implies 3 implies 1. Alright. So, 1 means it is invertible and 2 means A times the colon capital A colon Gotik A equal to A. So, A is invertible given. Suppose A is invertible, in FA, that means there is a inverse there. So, that is there exists A inverse in FA with A times A inverse equal to A. The other equality we do not have to write because we are in a commutative case. But this means what? This will mean in if we want to rewrite this, obviously we have to relate this A inverse with the colon. So, in the colon notation this means A inverse is contained in the A colon A. So, therefore, look at A capital A which is A inverse, this is the definition of the inverse, and now I am going to replace this with this containment. So, this is contained in A colon A which is contained in A. So, A is contained in A. So, all are equalities, therefore, we are done. So, all equalities and that proves 2. 2 was precisely this equality. Okay, 2 implies 3, so this is proved. 2 implies 3. We have given that A times capital A Gothic A colon equal to A, that is given to us, and from here we want to conclude that, what do we want to conclude? We want to conclude there exist elements x1 to x are here, y1 to y are here, which is 1, but that is trivial because this product of these two submodules is this, so 1 belongs there. So 1 is a combination of the product. So 3 is, this is trivial. 3 implies 1. So this we have proved. 3 implies 1. 3, what is given? We have given that there are elements x1 to xr in A and y1 to yr in capital A colon Gothic A with the x1, y1, etc., xr, yr equal to 1. Then we want to prove A is invertible. So look at the colon A times A colon A. This is, we know it is contained here by definition of this colon. So therefore this is an ideal in A, because it's a submodule contained inside A. So it's an ideal. So therefore and also we have given that there is x1 to xr, 3 says we have x1 to xr in A and y1 to yr in this colon, such that there this sums of the products, this is 1, that is given in 3 to us. So therefore this submodule or this ideal will contain 1. So 1 belongs to A colon AA. So we have an ideal where 1 belongs. So therefore that ideal has to be the unit ideal, which is the ring. So that proves this is equal to A. So that proves that A is invertible and this is the inverse of A, and the remaining thing is clear. The further that statement is just reorganization. So that proves 3 implies 1. All right. So let me deduce few consequences from here for the future use. So corollary 1, so remember this FA is the set of all fractionary ideals, and we have taken an A here. We have characterized when will this submodule of K has a inverse, and the condition 3 says that in particular it is finitely generated, because you see the third, this moreover part, further part says if A has inverse, then it is finitely generated by those x1 to xr. So therefore what we have proved, that I want to note a corollary, every fractionary ideal which is invertible is finitely generated. So an invertible fractionary ideal in A is finitely generated. See, there are many fractionary ideals which are not invertible in general. All right. So next, another corollary which we will use, that let A M be a Noetherian local domain then A is a DVR if and only if M is invertible. M belongs to FA cross, that is M is invertible in FA. Let's prove this. So, proof. So, this shows that you don't have to check for even if you check only the maximal ideal is invertible, then from there only you can conclude it's a DVR. Okay, so first we prove this way. Assume it is a DVR, then I want to prove M is invertible. If it is a DVR, then the maximal ideal is principal, but the principal ideals are invertible. The inverse is generated by the inverse of the generator. So, A DVR, first of all A DVR, that will imply M is non-zero and principal A times A, and therefore M inverse will be actually A inverse. So, this way is easy. Now, this way we want to check it is a DVR given that M is invertible. What does that mean? That means conversely, suppose that M is invertible. So, by the earlier lemma, that means what? That means there are elements here, R elements. So, there exist by lemma x1 to xr in M and y1 to yr in M inverse with x1 y1 plus xr yr equal to 1. But note that this xi times yi, this is in A for all I. Because x1 is in M and say for example x1 is in M and y1 is in M inverse, that means their product has to be go inside A. So, xi yi's are in A. So, and we know the sum is 1. So, that means at least one of them cannot belong to the maximal ideal. So, choose, because if all of them belong, all these products belong to the maximal ideal, then the sum will also belong to the maximal ideal, but one is not there. So, choose I such that, let us call it U, which is xi yi. This is not in M, but we are in a local thing. This element U is not in M, so that will mean that U belongs to actually a unit. U is a unit. Now, let us take any A. So, what do we want to prove? We want to prove A is a DVR. So, that means we want to prove that this maximal ideal has to be generated by a non-zero element, the principal ideal, non-zero element. So, I am looking for a generator for M. So, let us take arbitrary A in A or in M. Okay. Now, A equal to A U inverse, and U inverse is the inverse of this xi yi. So, I just multiply this. So, this inverse, so this is A, but this is same as I want to come out this U inverse is I have taken out, and then U inverse A, I commuted this yi and then xi. Where is this element? Obviously, this element I claim that it is in the principal ideal generated by xi, because for that I only have to check this is in A. This is in A is obvious because this A was where? A was in M, U inverse was a unit in A, therefore this makes sense in A, and this I multiplied by yi, but yi is an element in M inverse. So, elements of M times elements of F inverse go inside A. So, therefore, this element has gone inside A. So, this A is a multiple of this xi. So, therefore, and I have proved this for every A. So, that means this principal ideal generated by xi is M. So, it's a principal ideal, therefore, A is a DVR. So A is a DVR. Alright, I think the next we will prove that theorem next time.